Okay, welcome. We're going to be going over this problem today. This is the problem statements. Find the digits for the first digit, the factorial of a given non-negative number n. So the first step that we go about to understand or to develop a solution is we have to understand the problem. So how we go to understand it? So we have to figure out what the input is. The input is non-negative number n. And then what the output is the first digit of the factorial and first digits of the factorial. Then, so we have some examples here. So what kind of examples do we have? Let's just use examples that they give us here. So we have n equals 4. The output is 2. So why is that? If you multiply 4 times 3 times 2 times 1, then you get 24. And then you just take the first digit 2 here, and that's what the output is. And then similarly in this example 2, if n equals 5, the output is 1. Why is that? Because 5 times 4 times 3 times 2 times 1 is 120. And the first digit of 120 is 1, so the output is 1. So we have those examples. So I won't write them down, but the next thing we want to see is match kind of problems. So our similar problems are factorial problems. There's lots of those. And and also like digit patterns, anything with some kind of numerical extraction also. So extraction of digits. So we have those as matches, and then we want to plan. So how we're going to go about doing this. So we want to understand how to go about extracting the digits. So we could just write a function for factorial and just multiply through the entire sequence of n values and outputs, but the factorial gets very large, and so we will tend to not be able to store those numbers and will encounter some kind of overflow. So in order to plan against that, we can try to reduce the size of factorial and still maintain the fact that we can extract the first digit by, say, dividing by 10, for example, because we have something like this, since we know that x times y times 10 to the nth power is the same, has the same first digit as x times y, then we can store x times y instead of x times y times 10 to then. So in this sense, what we want to do is we want to compute factorial incrementally. So for I equals 2 to n plus 1, and each time we check to see if the factorial has a factor of 10 and reduce the function, the factorial by that factor. So Google Chrome wants the user confidential information. Okay, sorry about that. We have to go back to the CTI program. So how do I go there? We have history. So we want to go back here and we want to go to um guess we don't have it, so we have um, mm, improving was okay, let me just delete this. Okay, so we went, so sorry about that hiccup. So we got to the plan part of so we went to the understand match and then we got to the plan part of our solution. So we explained that x times y has the same first digit as x times y times 10 to the n. So we can store x times y as factorial instead of x times y times n. So each time we call x times factorial for I from 2 to n plus 1, we can reduce the factorial by um, by a factor of 10. So if you want to see that, and then and then and then we can remove 10 by integer division until we remain single digits, which is first digits in um, okay, so to implement this plan, we can do the following. We can ent enter the number n, which is an input, and then we can um, uh, range from, or we can set up the factorial, so factor effect equals 1, and then we can range from for I range n to n plus 1 or 2 to n plus 1. We can compute the factorial. Factorial is times equals I. And then while the factorial is divisible by 10, then we can divide the factorial into division by 10. And then so we're done with that loop. And then while factorial is greater than or equal to 10, you can, so there's one portion that we need to remind ourselves. If n equals 0, then print n, and print 1. And if n equals 1, then print 1. So for the rest of this, we're at the part where we have the string, or we have the factorial already, and then we're reducing by a factor of 10 each time, so that we can just take out the last element of, or the last digits of the factorial until we have one digit left, and then we want to print factorial. So there we have it. We passed all the tests out, the inputs. So the input 0. Oh, sorry, we have to like not go into this loop. So it's better to like put this into a function and return so it doesn't show up here. So I could write another if statement. So and is equal to 0 and 2. Oh, oops. I'll write left here. So there's one. And it passes. So we have this solution. So if we review this, we can go over here to Python tutor to review this. And then we can write 26 to be our number. So visualize what's going on. So we first have initialize factorial, and if n equals 0 or equals 1, then we print, but we don't print otherwise. And then we go through the range. So we start by um, multiplying out the factorial by I. So the first I is 2, and then and then it skips the while loop because there's no factor of 10. And then you keep on going. So it multiplies by 3 and 4 and 5, and when it multiplies by 5, then we get 120, which is a factor of 10. So it goes to the while loop and then uh, eliminates the factor of 10. And then it goes back and it just iterates over factorial or the factorial and increases factorial by each iteration of I. And we can continue on like that for some time until we get down to 26. And so once we get down to 26, we see that we go out of the for loop and we start subtracting out the digits of or the ones digits of this factorial. So we just subtract off the ones digit one by one if the factorial is greater than 10. And then after we reduce by each digit, then we end up with the last digit, which is 4, which is the first digit. And so we print that, and that's 4. And so we can go back and we can see what we did so far. So evaluation. Okay, so the evaluation of this is that um, uh, this is space complexity 01 because we don't take up any space. We have constant space consideration, and the time complexity is going to be O log n times n. We divide out these factors of 10. So that's about it, capping it up. We're just going to stop here. So thanks for listening.